Today we will look into a very important, we can say it is a very significant operational hurdle faced by blast furnace, particularly under monsoon condition. Monsoon condition introduce significant moisture into raw material, posing major operational challenges for blast furnace. Our primary objective is to produce molten iron continuously with high availability. However, excess moisture can severely disrupt stable operation, impacting efficiency, productivity, and longevity of the furnace itself. This presentation will outline these challenges and, more importantly, discuss a strategy to mitigate them. Now, coming to our next slide, which is about the core issue stems from the moisture entering the furnace with the raw material. Top charge burden material, including ore, coke, and fluxes, always contain moisture, which increases significantly during heavy rain due to outdoor storage. A major threat comes from fines such as ore fines less than 4 mm or coke fines less than 6 to 8 mm, because they can retain moisture and lead to accretion within the furnace. Even wet lump ore can carry piggy black fines, making proper screening very difficult. Crucially, any moisture charge into furnace must be removed in upper part before the reduction processes can effectively begin. To put this in perspective, approximately 33 kg of water per ton of hot metal is typically introduced with just 1% ore burden moisture and 5% coke moisture. Now, coming to talk about the operational impact, we can say that delayed reduction and thermal state, which are the main causes due to this moisture. Excess moisture has direct negative consequences on furnace operation and efficiency every time. Firstly, it causes delayed reduction and a decrease in productivity. Excess moisture delay the start of reduction, essentially creating a short furnace with insufficient time for reactions. This often necessitates a decrease in productivity to allow for increased burden resistance, and with the effect in residence time also, and at the same time drying time also. Secondly, we face a condensation evaporation cycle. Moisture in the furnace gas condenses on cooler part like cooled steps or freshly charged material, because the burden material are below the moisture dew point. This cycle critically drives the 100 degree centigrade isotherm downward, thereby reducing the metallurgically active area near the furnace wall and impeding gas reduction in the periphery. This leads to an increase in insufficient direct reduction, consuming uncharged coke and consequently cooling the furnace badly. Now, gas temperature and pressure. Let us focus on these. Beyond reduction, moisture impact gas dynamics and pressure immensely. Top gas temperature is significantly affected. A 1 mass percent increase in top charge S2O can lower top gas temperature by approximately 20 degrees centigrade, which is a big value. This can result in top gas temperature as low as 80 degrees centigrade, which is not desirable as far the dust catcher is concerned. Furthermore, extreme coke moisture variation due to rain or poor shortage can cause significant swing in the furnace's thermal state. This often activate normal thermal control procedure like the use of additional fuel. Lastly, excess moisture can increase pressure drop within the furnaces, especially in the upper part if fines agglomerate. This impede the smooth gas flow. As we know, that we have to maintain a constant pressure head in the furnace. Addressing these challenges begin before the material even enter the furnace. Effective screening is a paramount, and as we discuss in almost all our presentations regarding the importance of screening, we must screen burden material before charging to eliminate fines like breeze or fines less than 4 mm and coke less than 8 mm. Standard practice involves 5 mm aperture screen for burden material and 25 or 30 mm for coke in the stockhouse. Our target should be less than 3% fines below 5 mm after stockhouse screening, and this is supposed to be the index. We have to add in memory these particular data. 3% fines, 3% fines below 5 mm. This should be our critical boundary. Pre-screening in the stockyard is also crucial to remove piggy black fines not easily removed later. Raw material quality is the key. We must ensure overall burden quality, especially coke strength. Using a sinter and dry quench coke can reduce moisture in top charge material to nearly zero. Ideally, moisture content in charge material should be almost 0 to about 5 mass percentage 2O. Finally, bin and stockyard management prevents issues. Careful management of bin fills level prevent material breakdown and fines generation from long drops. We must also avoid using dated sinter or coke from the bin clearing as they have a poor permeability. A stockyard material can also have a different properties compared to freshly produced one. Now, coming to the blast air moisture control is also very important, and is it should be the standard practice of all operators. All blast furnaces plant inject steam into blast air to maintain constant S2O concentration, compensating for atmospheric humidity variation. This promotes steady and smooth operation and helps keep raceway adiabatic flame temperature constant. While moisture in hot blast doesn't consume coke, it can be an efficient method of thermal control for a hot furnace, increasing typically concentration from 15 gram S2O per normal meter cube to 25 gram normal meter cube will also raise the top gas temperature. We can also increase gas volume to eliminate water as a vapor and contracted the condensation evaporation cycle. We can increase the gas volume pattern of hot metal, for example, by injecting extra coal. Finally, adjusting top pressure can help. A lower top pressure allow the top gas to contain more water vapor at the same temperature, making smaller furnace more tolerant to high water load. The strategies regarding maintaining thermal stability and monitoring, we can say to maintain thermal stability, we should ensure a minimum top temperature, for instance, 110 to 120 degrees centigrade, or at least 90 degrees centigrade to prevent moisture accumulation and sustain healthy operation. Operator must anticipate changes from wet to dry material and adjust the coke rate accordingly to prevent rapid cooling. Circumferential symmetry is also vital for high performance. This means ensuring symmetrical wind distribution and symmetrical injection of coal and gas. Deviations such as a 2 year not injecting coal can substantially impact production and generate a asymmetric condition. For monitoring, we utilize tools like skin flow measurement and short in-burden probe, typically around 60 centimeter inside the hot phase and 3 meter below the stock line. This helps us monitor drying capacity and temperature changes caused by moisture. Now, beyond the operational efficiency, moisture poses a severe safety risk. Water leakage is exceptionally destructive to refractory lining, as we all know. Leak can occur from a failed to-air cooler, staves, and cooling plates. The water then migrates into the refractory lining, tracking downward into the hearth, potentially oxidizing carbon-based refractory and forming punky carbon. Significant water leaking can also drastically increase temperature and form material accumulation. The most critical hazard is explosion risk. Water leakage into the furnace poses significant risk of water, molten iron, or slag explosion. Intensive water injection can lead to knocking or explosion by causing too much water to decompose into explosive water gas, that is a hydrogen and oxygen, when contacting hot coke. Catastrophically, if hot metal covers water, an explosion can occur immediately due to the rapid conversion of water into expanding steam. Now, coming to our proactive and prompt action, thus are essential to manage these hazards. Firstly, we must promptly renew broken tuyeres and ensure cooling water is controlled without leaking into furnace. It is crucial to avoid cutting off cooling water to leaky tuyeres as this accelerate damage tremendously. Secondly, for water spray at the top of the furnace, special water atomizing nozzles are required. This prevents water from directly touching or reaching the burning surface or flowing down the wall, mitigating direct control and potential hazards. Now, in conclusion, effective management of monsoon condition is critical for stable and efficient blast furnace operation. This involves a multifaceted approach, starting with proactive measure to minimize moisture input in raw material through screening and strategic storage. It also requires dynamic operational adjustment within the furnace, such as a precise control of blast air moisture, gas volume, and top pressure. Vigilant monitoring and prompt intervention are essential to mitigate the negative impact of moisture on furnace thermal state, reduction efficiency, and gas flow. Most importantly, strict adherence to safety protocol is paramount to prevent water related hazards, including explosion and refractory damage. By implementing this comprehensive strategy, blast furnace operators can ensure a smooth furnace operation, reduce fuel consumption, and extend furnace campaign life even under challenging monsoon condition.